It's just the two of us so far, so I am going to start. Let me just see. Don't know if
Hi,
anyone
Mom.
else is going to join. You can just stop me if you have any questions. You can just unmute your mic and then speak if you want me to stop.
Hi, Mom.
Hi. Okay, I'm going to get going with A. Right, so they're saying, let me just get to everything quickly. So I just want to make sure. Okay, no one else is waiting to come in. Okay, they are wanting us to prove this one. 2 plus 4 plus 6 plus dot 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 plus 2n. And that is equal to n times n plus 1. Okay, so they want us to prove this one using mathematical induction. So the nice thing about this is that they've already written out the required to prove part for us in mathematical terms. So we don't have to worry about that. So our first step is going to prove this for n equals 1. Sorry. In this case also, yeah, they're not stating in each question that n is an element of natural numbers, but they stated that in like the heading of number 2. So we can just assume that for all of them. So for n equals 1 on the left-hand side, that means that we're just going to work with our first term, which is 2. So the left-hand side will be equal to 2. And then the right-hand side is 2. Oh, is this whole thing? So it is n times n plus 1. So instead of n times n plus 1, we're going to say 1 times 1 plus 1. So we just have to show that substitution as well, so that they know that we're not just jippering the system. All right, so the right-hand side is also equal to 2. So now we can say, therefore, left-hand side equals right-hand side. Therefore, true for n equals 1. Okay, so that's the first part that's done. Then we have to say, assume that it's true for n equals k. So assume true for n equals k. So now we're going to rewrite this whole statement. Just instead of n, we're using k. So we're going to say 2 plus 4 plus 6 plus dot 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 plus 2k is now equal to k times k plus 1. All right, and we're assuming that that's true, so we can then use it in our next statement. So now we have to say for n equals k plus 1. So now we're going to rewrite this whole thing, but 2k is now going to be our second to last term, and our last term is going to be 2 times k plus 1. Okay, so it's going to change slightly. We're going to have 2 plus 4 plus 6 plus dot 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 plus, and now we're going to include the second to last term, and then our new last term is going to be 2 times k plus 1, like that. I keep forgetting to put in left hand side equals, oh gosh, okay, so that would be our left hand side. Sorry about that. For the next one, hopefully I'll remember. Then our right hand side, instead of k, we're going to have k plus 1. And instead of k plus 1, we're going to have k plus 1 plus 1. So this is going to be k plus 2. Okay, so we need to prove that this is equal to that. So now I'm just going to do it in pink again, like I did in the note. This whole statement appears in my new statement. So I'm going to substitute that expression in for the underlined statement. So we're actually going to say equals, instead of the underlined statement, I'm going to write k times k plus 1. Plus, then what was left there is 2 times k plus 1. Now from here, we can see that we have a common bracket. So we're going to take that bracket out as a common factor. And from my first term, if I take that bracket away, I'm left with k. From my second term, I'm left with plus 2. Sure, that's actually such an easy one. So that is then equal to the right-hand side. Okay, so now from here...
Sorry, Vicky. I got this one.
Oh, nice, thank you.
See,
It's fine.
and I know it's against the law.
It's okay.
Break the law, break the law.
Sorry about that. Okay, so now we just have to do that last where we like list all of that stuff. So now we're going to say therefore, what was that whole thing now again? Now I can't remember. True for n equals k plus 1 if true for n equals k.
Hold on, see.
Mm-mm.
From here.
And true,
How many are there?
just one, just Iman.
Well done, Iman. I'm very proud of you. I don't know you. You're going to make
Thank
a woman very happy.
A woman.
Oh, man.
She's saying hello, I think. You heard a lot of Iman. She was on my basketball team.
I know.
Mm.
She's very famous in your word bank.
Okay, so now and true for n equals 1, then true for n equals 2, n equals 3, and so on. Therefore, true for all n element of natural numbers. And that's it. Is that one fine?
Yeah, that was an easy one, so it was okay.
Okay. Yeah, and this last bit is a bit annoying because you have to write it every time, but in a test or exam, you'll only get one of these. So hopefully you'll only have to write this down once. Okay,
Yeah.
next one was C. Okay, let's get going on that one. C, 11 plus 15 plus 19 plus 4n plus 7, and that is then equal to 2n squared plus 9n. Okay, so that is now the one that we need to prove, again using the same method. So we're going to go again for n equals 1. The left-hand side is going to be 11. And then the right-hand side is 2 times 1 squared plus 9 times 1. So 2 plus 9, which is also 11. Therefore, LHS equal to RHS. Therefore, true for n equals 1. You're still the only person. I wonder if anyone else has actually done it. Okay, and then we need to assume true for n equals k. True. N equals k. So now we're just going to rewrite the whole thing. So 11 plus 15 plus 19 plus, and then we have 4k plus 7 equals 2k squared plus 9k, like that. Then for n equals k plus 1, left hand side, finally remembered, equals 11 plus 15 plus 19 plus, and now our second to last term is going to be this, 4k plus 7, and now our last term is going to be 4, and then this is going to become k plus 1. So we can just kind of visualize that. So it's going to be 4 times k and 4 times 1. So 4k plus 4 plus 7. So that's going to give us 4k plus 11. All right, so that is the left-hand side. Now I don't have quite enough space for the right-hand side, but I'll just like try and squeeze it in here. The right-hand side is going to be equal to 2 bracket k plus 1 squared plus 9 times k plus 1. And now we can simplify this. I'm not going to multiply the brackets out here. I'm not going to square this out because I do have a common bracket. So what I'm actually going to do is I'm going to take out k plus 1 as a common factor. And then on the side, oh, my spacing is way off, sorry. But on the side, then I'll be left with 2k plus 1 plus 9, like that. And then I can simplify that. It's going to give me k plus 1. And then 2k plus 2 plus 9, so 2k plus 11. I hope that's correct. Let me just double check. So the right-hand side is 2k plus 1 squared plus 9 times k plus 1. Then I took that out as a bracket, common bracket. I'm left with this plus 9, 2k plus 2 plus 9. Okay, so this is an easier thing to work towards, I think. We'll see how it goes. Now here on the left, again, that statement is that statement. So we're going to substitute this with 2k squared plus 9k plus, and then this is now 4k plus 11. And that is then equal to 2k squared plus 13k plus 11. Okay, so I suppose if you multiplied this out, then you also could have just got into that step, which actually would have been fine if you just multiplied it out and you got 2k squared plus 13k plus 11. But I'm assuming, I'm going to check it now, but I'm assuming that if you were to factorize this, you would get this. But let's just double check that quickly. Actually, I can just multiply it out. So that's 2k squared plus 2k plus 11k, which does give you 13k, and then plus 11. Okay, so it does simplify to that. Factorize to that, rather. Okay, so then equals RHS, and then therefore, blah, blah, blah. I'm not going to write all of this down now. It will be exactly the same as up there. Okay, I'll write it down before I actually post the answer. All right, that one also not too bad. Fine with that one?
Yeah, that was fine. I just I wanted to know if you could simplify the right hand side and the left hand side, but you did, so it was okay.
Yeah. So it doesn't actually matter in which way you write them as long as you get them to be equal to each other. So what I've seen some people also doing is, suppose it's not really relevant for this one, but some people will only work like almost halfway on this one and then like they'll do some more stuff on that side and then get them to be equal like that as well. Okay. The next one was E. So let's see. Okay, E. And I think this one is a bit more complicated. And then G looks not very nice, but okay. Okay, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus, okay, we have n times n plus 1. That is equal to n over n plus 1. Okay, for n equal to 1. So that just means that we're using our first term. So this, if we simplify the first term, would just be equal to a half. So the left-hand side equal to a half. There we go. And here, right-hand side. So now we're just going to sub n equals 1 in here. So 1 over 1 plus 1. That's 1 over 2. Like that. Then assume, oh, sorry. Sure, I'm just jumping the gun here. I actually first need to say, therefore, left-hand side equals right-hand side. LHS equals RHS. Therefore, true for n equals 1. Okay, now assume true for n equals k. So we're going to say 1 over 1 times 2 plus 1 over 2 times 3 whole thing plus, and then plus, and now just instead of n, we're going to write k. Okay, like that. Now for n equals k plus 1, I'm going to rewrite this whole thing. This is now again going to become our second to last term. So we're going to say LHS equals. And I'm just rewriting it in the same way, like showing the multiplication here, but it actually would have been fine, I think, if you just multiplied these numbers together. The only reason why they wrote it like this is so that you could actually see that this is the like general term of getting 1 times 2, 2 times 3, 3 times 4. It's always a number multiplied by 1 plus that same number. So yeah, but I think it would be fine if you just wrote it as the actual simplified fractions. Times 4 plus dot 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 plus. Okay, now this one becomes our second to last term. Plus, yeah, but I can. And then the next one, so now for this, k plus 1 is going to be in the place of k, so k plus 1. And then k plus 1 is going to become k plus 2. Like that. So that is the left-hand side. And now I really don't have space on the side here, so I'm just going to write at the bottom, actually. Right-hand side equals. So we need to prove that now this, but instead of k, we're going to have k plus 1. So at the top, it's going to be k plus 1, and at the bottom, k plus 1 is k plus 2. Okay, so that is what we need to prove. So now I'm just going to state again, left-hand side equals, again, this whole thing is that statement there. So I'm going to write here k over k plus 1 plus, here we go. Sure, I just had like a moment where I didn't know what I was doing. Okay, there we go. And that is 1 over again. So now we can see that we're adding two fractions together. So we're going to have to write them over the LCD, which is going to be k plus 1, k plus 2. So this I must multiply by k plus 2. And that means that that one I must as well, in brackets obviously. So we're going to have k times k plus 2 plus 1 over k plus 1, k plus 2. Then we multiply out, so that's going to be k squared plus 2k plus 1 over that. And now this trinomial is going to factorize to k plus 1 squared. Okay, so that's what we do at the top, k plus 1 squared. And unfortunately, because this is like a prove that or show that kind of question, we have to actually show all of our steps properly. We can't really skip any steps out. So k plus 1 over k plus 2. And there we go. That's what we're supposed to get to. So that is equal to the right-hand side, and then therefore, and then again that whole long thing. Okay, last one, G. This is my old note. Here we go. There's a blank. All right, so G, they've given us something in sigma notation. So sigma, and now we're not using I, actually we're using P. So from where P is equal to 1 to N of 1 over 2 to the power of P. And that sum should be equal to 1 minus 1 over 2 to the N. Okay, so now our RTP thing, our required to prove thing, we do actually need to write down. So we need to remember that this sigma means the sum. So to get our first term, we're going to make P equal to 1. Our second term, we're going to make P equal to 2. Our third term, we're going to make P equal to 3. So we're going to have 1 over 2 plus, and you can leave it as 1 over 2 squared if you want, or you can go straight to 1 over 4. That's also fine. And then 1 over 2 cubed plus dot 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 plus. Now, if the last term is n, then that means that we're going to have 1 over 2 to the n as our last term here. We must always just show the last term as well. And now they're saying that this is equal to 1 minus 1 over 2 to the n. Okay, so now because they've given us this thing that we need to prove in sigma notation, we do actually have to write that line out first. Okay, so for n equals 1, we're going to say a half. Oh, sorry. What am I doing? Feeling a bit distracted. Sorry. So for n equals 1, the left-hand side is equal to a half. There we go. And then the right-hand side is going to be equal to 1 minus 1 over 2, which is a half. Therefore, left-hand side equals right-hand side. Therefore, true for n equals 1. Okay, next up, assume true for n equals k. Assume true for n equals k. So half plus, I am actually going to just use the actual values here. Just check that quickly. Oh. Okay, so this one we assume is true. Then we're going to say for n equals k plus 1. Left-hand side equals a half. This one is now our second to last term, and our new last term is now this. 1 over 2 to the k plus 1. So that is the left-hand side, and the right-hand side I will be able to fit in here, luckily. It's going to be 1 minus 1 over 2 to the k plus 1. Like that. Okay, so we need to prove that this is equal to that. Again, same thing. I'm just going to keep underlining this whole thing. There we go. So that is equal to that. Oh, lovely. How nice. What we're going to have to work with now. So this 1 minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Okay, so now we need to somehow prove that this is equal to that. So what I suggest is that we break this up, because 2 to the k plus 1, and this might now be me taking like a long route, I hope not, but that's the same thing, right? So 2 to the k plus 1 is the same as this. So if we have it written in this way, it's a bit easier to see in order to write it like over an LCD. It's a bit easier to see what we actually need to multiply by. So I'm going to try that. I'm going to write all of them over an LCD and see what happens. We might be able to factorize or something from there. So that means that if this is the LCD, I'm going to write it separately. Again, I apologize if I'm a bit on the wrong track here. I hope not. So it would give us that. That would be the first term because it's just 1, so that divided by itself. Here we would have, since the LCD is this, we need to multiply it by 2. So the top is also going to be 2. So we're going to have 2 to the k times 2 to the 1. And at the bottom, at the top, we're going to have 2. Sorry, at the bottom, we have 2 to the k times 2 to the 1. At the top, we have 2. And then we have plus 1, 2 to the k times 2 to the 1. So now, okay, so this is now what happens. This one we actually could have just left as 1. Because we now have these two, because we're looking at what we're trying to prove, right? We do have a 1 minus in our right-hand side. So we actually could have just left that as 1, okay? But it's fine. We were just like experimenting. Now we need to get negative 1 over 2 to the k plus 1. Now here we have minus 2 plus 1, and they have the same denominators. So we can actually do that then. So these are then actually like terms. So negative 2 plus 1 is negative 1. Okay, so I'm going to take this one back to just being 1. So if you had noticed that from the start, obviously you could have just left that as 1 straight away. And then you would just have minus, and yeah, let me rather not. Just minus 2 plus 1 is negative 1. And then I'm just going to change that back to 2 to the k plus 1. Okay, and that is equal to the right-hand side. And then again, therefore, blah, 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 all of that stuff afterwards. Okay, is that all right?
Yeah, I had a little bit of trouble with this one because it was like complicated at the end, but it makes sense now.
Okay, no, I'm glad. Yeah, it's so these questions, the most difficult part is actually this like algebraic manipulation kind of thing. And they can ask it in so many different ways, so it can sometimes be a bit tricky. Okay, you didn't have to do any of the other ones. We are going to look at number 3 now quickly. But I'll also post this on the group, but the others are now going to be homework for Thursday. So you did A, C, E, and G. So now B, D, F, and H are going to be, you're supposed to do them for Thursday, and I'll just post the memos for that one, or for those ones rather. Okay. Number 3. I haven't actually done this one. Let's see. Okay, so Jerry wants to prove the formula that is sometimes used in the Riemann sum. Okay, so this one. And then they've written the RTP part. So 1 plus 8 plus 27, and then n cubed is equal to this. So he does the following steps. Let n equals 1, and then the left-hand side is 1, and the right-hand side is 1. Okay, therefore the statement is true for n equals 1. Correct. Let n equals k. So what I think the mistake there that he made is that he was supposed to assume true for n equals k. Right? So 3a, you mustn't just say let n equals k. You actually have to say that it's true so that you can use it in the next step. So let me just check here, write the correct version. So it would just be assume true for n equals k. Okay, and then after that, in step 5 is where he actually listed it, which is fine. Then for B, they're saying Jerry could not finish step 8. Write down this part of the proof. Okay, so for step 8, So step 7 is where he's showing the right-hand side, and then step 8 is the left-hand side calculation. So that would now be taking this one, and instead of k, having k plus 1. Okay, so that would be the first part of step 8. So you would have to say left-hand side equals 1 plus 8 plus 27 plus dot dot dot. And then I'm going to rewrite this k cubed because it is now the second to last term, and then k plus 1 cubed equals, so in the n equals k line, it's k squared, which is now going to be k plus 1 squared. And then they have k plus 1 squared, which is now going to become k plus 2 squared over 4. Now, why am I doing that now? This is the right hand side. Here we go. Okay, so this actually, I'm not going to erase it now, but this would be the right hand side. It is maybe good if we have that. There we go. That's actually not a part of it. It's just that. Okay, then this is what we're going to now substitute this for. All right, so we're going to sub in that because 1 plus 8 plus 27 plus k cubed, so what we have there, is equal to that expression. So we're going to say k squared bracket k plus 1 squared over 4, okay, and then plus this, plus k plus 1 cubed. Now same thing, we're going to have to put it over an LCD, which is going to be 4 in this case. So we're going to have k squared times k plus 1 squared plus 4 times k plus 1 cubed over 4. So that's going to leave us with, so now we see that we have k plus 1 squared is now common. So we're going to take that out as a common bracket. And then here we're left with k squared. Actually, I should use a square bracket there rather. So here we're left with k squared. And then in our next term, we would be left with this. Okay, and that is all over 4. Right, equals k plus 1 squared. And now here we're going to multiply this out, obviously. So we're going to have k squared plus 4k plus 4, which is a perfect square trinomial. So when we factorize this, we're going to get k plus 2 squared. So there we have k plus 1 squared. And then this factorizes to k plus 2 squared, and that is all over 4. Right, and then I'm just going to add here equals right hand side, and then in their thing they say that step 9 is conclusion, so they're not expecting us to write down those conclusions. Okay, and that was it. Do you have any questions on this one?
No, this one was okay. I just had a question on when you did the lesson, there was a part where it said k is an element of real numbers. Do we have to write that?
Let me just check. I remember that here. I think I said that you do. Let me just check, where did I write that for the first time? I can't find it now.
I can't remember where. I think it was in the first example.
Okay, so it's here.
On the third step.
Oh, there. Okay, yes, I see. Yeah, I actually think that you don't have to, because these because they state, I think I just wrote it because it was the first example and I just wanted to make that clear. I can't remember now how I worded it. But in these questions, because in the question they're saying that n is a natural number, if you are then saying that n is equal to k, you are saying basically that n can only be a natural number. So now if you're making that equal to k, then it's basically implied that k also has to be a natural number. If that makes sense, I hope.
Yeah,
So
it makes sense.
you can write it in, like they'll never take a mark off if you write that down. But I also, now that I'm thinking about it again, they also won't take a mark off if you don't, because it is implied by even the question. Okay.
Okay.
All right. Thank you, Iman, for joining me.
No problem.
Okay, I hope that helped.
Yes, it did. Thank
All
you.
right, I'll see you tomorrow. Hey, which group are you in?
Group 2, so the later one.
Okay, I'll see you then. Thank you.
Okay, and then Grace also says that she's just moving house, but she is going to watch the video on YouTube.
Okay, great. Shame, that's fine. Thank you so much.
Okay.
All right.
Bye.